All right. And just 1 second. Let me share my screen right now. Okay. So let's talk about the material extrusion 3D printing process. So this process is the most widely used 3D printing process in the world. And as I mentioned previously, it is invented and patented by Scott Crump around 1988. Basically, Scott found the Stratasys, which is a main player in the 3D printing area. So what this process does is it first soften the thermoplastic material and then extrude those material onto the substrate. And then once one layer is built, another layer is added on, and so on and so forth. So that's the how the material extrusion look like. So it's somehow like making a cake, right? It very similar. Basically here shows you a illustration figure of material extrusion. And this is a kind of simulation of all the layers in the software. This here shows the tool paths of each layer, which will be executed by the printer. All right. Let's look at a video.
Fused Deposition Modeling, or FDM, is a layer additive manufacturing process that uses production-grade thermoplastic materials to produce both prototype and end-use parts. This technology is known to accurately produce feature details and has an excellent strength-to-weight ratio. FDM is ideal for concept models, functional prototypes, manufacturing aids, and low-volume end-use parts. The FDM process begins by slicing 3D CAD data into layers. The data is then transferred to a machine, which constructs the part layer by layer upon a build platform. Thin thread-like spools of thermoplastic and support material are used to create each cross-section of the part. Similar to a hot melt glue gun, uncoiled material is slowly extruded through dual heated nozzles. The extrusion nozzles precisely lay down both support and thermoplastic material upon the preceding layers. The extrusion nozzle continues to move in a horizontal XY plane while the build platform moves down, building the part layer by layer. The finished part is removed from the build platform and cleaned of its support material. Raw FDM parts have visible layer lines. However, service providers such as Solid Concepts offer multiple finishing options to create smooth, even surface parts including hand sanding, assembly, and cosmetic paint. Since FDM parts are constructed with production-grade thermoplastics, including ABS, polycarbonate, and Ultem, they are both functional and durable. FDM is utilized in a number of industries, including aerospace, automotive, industrial, commercial, and medical.
All right. So let's move on. So as you can see, the material utilized in
Professor Fan, sorry, I have a question.
Oh yeah.
We are going to see techniques to polish the final pieces in FDM. in this course or in the lab sessions, maybe, or not? To
What
polish
was the
the,
question again?
we are going to see different techniques for polish for the final yes, for the final appearance of the prosthesis, but for FDM process, because the in the video you show to
Yeah.
us, it's different when you use techniques to polish and use, I don't know, maybe chemicals or something like
Yeah.
Mhm.
So you're asking, are you required to do such polishing, or?
Yes, if maybe in the labs we can see some of these different techniques to
Okay.
finalize the
Yeah. Oh, that's a good question. I think definitely some of them you are certainly can do. That is, for example, using the sandpaper, right, to smooth it. That's definitely possible. And also the paint. Basically, you just purchase some cosmetic paint and just paint it, right? And for some other ones like the vapor, the solvent vapor, solvent vapor, that's for ABS material, which is not the one we used in our lab. So basically, the material we use is as the PLA material, which is not applicable for such a treatment. So I think for that, probably we are not able to do it, but definitely sanding and also as well as the painting, it's possible. I mean, if you want, definitely, you can do it for your own prints, right?
Thank you.
I have a question.
Yeah.
Good morning. There's like this gray block in front of the text now. Is there any way you could remove that moving forward? Like,
How about now?
Yeah. Do you see this?
Okay. Oh, yeah. I think that's another window. I just remove it. Okay, thank you. All right. So yeah, any other questions? No. Okay, good. The material we use is thermoplastic, and it's in the form of filaments. Basically, normally those filaments has a diameter 1.75 millimeter or 3 millimeter as a diameter. The nozzle has different size as well, typically from 0.4 to 0.8 diameters. So it cannot be arbitrary numbers for the nozzle's diameter. It's in multiple of 0.1 millimeter, right? That's a very interesting point you want to keep in mind when you have little maybe questions. For example, that could be a question asking you, okay, can we have a 0.45 millimeter diameter for a nozzle? From this, you should be able to answer, okay, that's not possible, right? So the centric part for this printer is the hot end. So basically, this hot end will heat the plastic enough to such that the melt plastic could flow through the nozzle. And there's a thermometer or thermocouple to measure the temperature. If you look at this figure, basically here it is the thermistor or the thermocouple located. Basically, it will monitor the temperature, and basically that will be the one you play with. I mean, in the software, there are options to choose different temperature, and with different temperature set, different material could be used in this process. But how to control the temperature? You have to monitor the temperature. So these thermistor and thermocouple are for this purpose. And also there's a heat sink. See over here, this is the heat sink. So this heat sink will prevent the heat from the from conducting up the filament and cause problem. Basically, here is the feed tube. There is a filament here. So what you want to have is in this region, those filament will be melt and it flows through the nozzle. But other than that, in this region, you want to keep the filament a solid state. In that sense, you want to prevent the heat in this region to be conducted and melt the material in this tube, I mean, in this region. So that's why this heat sink is utilized to prevent the heat conducting. Usually there will be a fan to further kind of prevent the actual heat. And so that's another component which hasn't been shown in this figure. But if you look at the hot end on the Poisson machine we have in the lab, it has a small fan to blow the heat air and further prevent the heat conducting. All right, that's the hot end. Actually, for different 3D printer, there are different appearance. For example, some of the printer has this kind of chambers. So what's the function for this chamber? That is because the printed material will shrink during the printing. Because when its temperature drops, there will be a shrinkage. So therefore, the part have a tendency to curl up at the corners. So let's look at this illustration figure. All right, we have one hot layer, right? That's the one we are depositing, and usually this hot layer will be deposited onto a cold layer, which is deposited previously. So as you can see here, this is what you have currently. Because this cold layer has a lower temperature, it becomes to shrink. And there's different ratio for the hot layer and cold layer for the shrinkage. Therefore, you will have this curl happens. That's why there's a curl for your layers, for your prints, especially near the corners. So a heated chamber is used to reduce this tendency of parts to curl, because within this inside this chamber, the temperature is maintained to a higher level, such that even this new previous built layer will be in a high temperature. That will effectively prevent the curl during the printing process. And also, you will have different build platforms like plastics or glasses or aluminum. And sometimes you want to use tapes or glue to bond the first layer of your prints. That's why if you use the Poisson machine, the first step is to put some glue onto the printing platform. That's for the better bonding of your prints. Then we talk about materials. As you can see here, there are quite a bit different materials for the material extrusion. As I mentioned, the PLA material, right, which is what we use which we will use in the in our lab. And another commonly used ones, ABS materials, and also some PETG materials and nylons. There are some flexible materials which can be used to print some flexible parts. There are different properties for this material. For example, the stiffness, durabilities, and strength, and so on and so forth. So you want to look at these when you decide which material to be used in your prints. Another factor which is also important is the printability. Basically, it describes how easy or how difficult to print using this material. As you can see here, apparently PLA and the PETG has a really good printability. But for some other material like these flexible materials, it has smaller printability, which means you probably need to be careful when you use such a material. Also, the temperature setup will be different for different materials, right? And you want to heat up the printing bed as well, and there's a setup on the bed material. I mean bed temperature. So that's the important thing you want to look at when you use the printer to print using different materials. Then,
Professor,
yeah, go ahead.
is a heated bed always required in a print?
Well, that's almost a requirement. That will greatly reduce the chance to have a unbounded prints. That means the part could move during the printing. So usually you want to heat up the bed. That is also because if the temperature of the printing bed is too low, that will reduce the bonding between the first layer and the bed. Also, that could cause the curl as well, because it will cool down the first few layers if the bed has a lower temperature. So that's usually a recommended setup.
Okay.
Right? Yeah. So another components for this printer is this filament feeding mechanism. As you can see here, that's one such a feeding system. I think there's something wrong here. Yeah, these tags are not related to the figure. I will correct it, but that's a small issue. So for the filament feeding mechanism, that could be here shows a typical setup. As you can see here, this filament will be driven by these two rolling screw to fit in through this hole, right? That's how it works. But it will only work well for those rigid material, like the SLA material. But how about some flexible one? As you can see here, for the flexible one, there could be easily happening problems. That is, well, the material cannot be fitted into the hole, and it will be something like this. There will be actual material fitted, and that could cause a jam during the printing. The reason is there is a distance. Let me clean this up and point out where it is. Basically, from this to this to this hole, there is a distance, and because the material property of this flexible material, it's very hard to fit them directly into a small hole. Therefore, a better solution for this kind of feeding setup would be if you just directly connect this part to the hole. That will solve this problem. Basically, you just minimize the distance, and this is a better solution, better design for sorry, for feeding these flexible filaments. All right. And again, for this feeding mechanisms and hot end, there are different setup. One is the so-called direct drive, the direct drive system. Basically, the filament feeding mechanisms is connected with the hot end. So that's the direct drive. Or there are Bowden filament feeding. So that means the feeding system is here, but the hot end is here. So they are separate. There are both pros and cons for direct drive and Bowden drive systems. So first of all, if you have a directly drive system, it's actually provide a more reliable filament feeding for variety of materials, such even for the flexible ones. So it has a less chance to fail if you use a directly drive when you use flexible materials. But for the Bowden one, well, there are quite a bit problems when using this to print the flexible material. And even with the rigid material, there could be a jam because the distance between this and the hot end is very, very, very long, very far distance. And during in between of this, there are possibilities. For example, this has a problem or this has a problem, and it turns out it will fill this printing together, right? But the benefit for have a Bowden filament feeding is you are removing weight from this hot end. And this hot end will be the movable part to print, right? If the weight of this printing end is in lightweight, that has a benefit to the control of this hot end. And that will make the control easier and make the accuracy of the movement higher. And that's a benefit for the Bowden filament feeding. All right. So you can see both of the two feeding or driving systems on different fused deposition modeling printers. So there is another setup you want to play with in the fused deposition modeling printing. That is the toolpath. So a part to be printed using fused deposition modeling is not a whole solid part. Actually, there are some hollowed regions, and also you need to look at how you want this hollowed region look like. And that's the infill. So in each layer, instead of printing a whole solid layer, you could print these patterns. There are different patterns for you to choose. Also, you could choose different percentage for the infill. It could be 20% and up to 80%. So the interior region of the part is not 100% dense. So the lower density actually saves quite a bit of material and reduce the part weight. But at the same time, the part strength is not weakened because we after the testing, we figure out actually the skin contribute the most in the rigidity. So different infill actually will only impact quite little on the part strength. Also, even the different percentage has very little impact. I think you can play with different options when you do the lab sessions. Try like 20%, 40%, 60%. But remember, the more dense you choose, the longer time it will take for the printing. All right. Actually, the simple linear rasterizing is the chosen most all the time. That is this one. So this is the most widely used filling patterns. I mean, but there are some research recently looking at besides these built-in patterns, can we optimize the infill by checking the load this part will take and do some topology optimization for each of the layer, such that there are customized infill for each layer, and it is expected to be the optimal one for the infill. But that's not what we are looking at this moment, and it is still in the research stage. Hopefully, there will be some practical enough solutions for the software in the near future. So as I mentioned, the Stratasys is the main player in the fused deposition modeling area. So as you can see here, there are different models for the printer, and you can see all of them have the chamber. Again, that is for maintain a higher temperature during the printing to prevent the curl of the layers. So a essential question for these printers is, what is the achievable accuracy? So is the accuracy for X, Y direction, X, Y plane, and Z direction the same? Anyone can give me an answer. Yeah, you can just anyone? Okay. Basically, if you take a look at the printer, you will realize actually the accuracy of the prints for XY plane is higher, much higher than the accuracy in Z direction. So that gives you I would say a constraints when you think of how you want to print your part, because the higher accuracy is in the XY plane and the lower one is in the Z direction. So in that sense, if you want to print some parts and you really want to achieve a high accuracy in certain direction, then you want to orient the part in such a direction that will be printed in the XY plane. So that essentially prevents the lower accuracy for your prints. So that's one factor you want to think of when you decide how you orient your part during the printing. So if we look at those menus for printer, you will always see two set of numbers. Basically, for example, let's see we have some description in the menu like this. So the parts are produced within an accuracy of positive negative 0.127 millimeter or positive negative 0.0015 millimeter per millimeter, whichever is greater. So how you understand this? Why there are two set of number? And also for this one, for this number, the unit is also interesting, right? You have a minute over minute, right? minute per minute, I mean millimeter per millimeter, sorry. Why there's a unit like this? So actually these two number represents the two error sources or for the prints. So the first number gives you the inaccuracy or the error from the nozzle size, right? And the second number suggests the printing error from the shrinkage of the parts. So that means per millimeter prints, there will be 0.0015 millimeter shrinkage. So that's why you have these two numbers. So if we look at a specific part, for example, a part has which is 100 millimeter long, then what will be the tolerance for the dimensions prints with the machines? So if you do a little computation, so what you will do is you have this long for the part, then you could compute what will be the error brought by the shrinkage by checking this. So you have 100 millimeter long, then 100 times this number. That will give you the error from the shrinkage of the part, which is 0.15. So again, you check this number and compare it with this error, right? This error is from the nozzle size error, and you figure out this one is larger than this error. That means the shrinkage dominate the error. Then the accuracy, you need to choose the larger one. That means it can only achieve such level of accuracy. So that's how you come up with an error for this part. But how about you have a smaller part which has a 10 millimeter length? Again, use the 10 millimeter and this number. You will figure out the error for from the shrinkage is less than the first error. Then you choose the first error as the accuracy. That means the dominant error is from the nozzle size instead of the shrinkage. And that's, I would say, intuitive to understand, right? Because this shrinkage actually is proportional to the length or the dimension of the parts. If the dimension is larger, it will bring larger error to the prints. And it turns out this error will be larger as well. So for larger parts, the shrinkage of the part will dominate the accuracy instead of the printing head. But why there's a printing head or nozzle size error? If we look at this illustration, you should be able to understand. For example, you have a nozzle size 0.6 millimeter, and you want to print a, I'm sorry, if let's say you have a nozzle has a 0.4 millimeter, right? 0.4 millimeter size. And you have a part which is 0.6 millimeter in the length. So how you print it, right? You either print two lines of the material such that it turns out you have a 0.8 millimeter for the dimension to represent, to approximate this part, which has a 0.6 millimeter dimension. Or you just print one line of the material, which is 0.4 millimeter in dimension, to approximate the part again with 0.6 millimeter. So you will have either a positive 0.2 millimeter error or negative 0.2 millimeter error. So that's how this nozzle size will bring errors to your prints. That is, you can only print the multiples of the nozzle size, nozzle diameter for the dimensions. And sometimes you cannot reach the exact dimension of the part, and there will be an error associated with this. All right. Any question regarding this slides? No.
I have a quick question.
Yeah.
I don't know what assignments or I guess exams or
Yeah.
even I guess quizzes will look like in the layout of this class, since we like don't meet in person outside of labs.
Yeah.
So is this, I mean, these are quantitative values. Is this something that we can expect in some kind of examination or homework assignment, or how will that be like laid out?
Yeah, good question. Yeah, there will be computational questions as well as some right or wrong questions. Basically, the computational ones will be based on some of the knowledge we introduced during these lectures. And it will give you numbers and setups. You need to compute the exact solution, exact numbers. Or there is some basically give you a statement, tell me which is wrong, which is right, something like this. And I think it depends on our progress. That could be the first assignment after this class, or if we cannot complete the lecture, that will be the one probably next week, right? But next week is there's no class, right? Then probably the week after next week. But there will be roughly each of the topics, there will be one assignment associated with it.
Thank you.
Yep, no problem. But don't worry, basically all the computations you will do, or all the knowledge you will be using for solving the assignment will be on the slides. There will be an example somewhere. So you won't have a question has no reference, right? That won't happen. Okay. So as I mentioned, basically in the video you also see some post processing to fine tune the surface, and there's a special one which is the vapor smoothing. So basically, it is for some of the polymers such as ABS, and basically you just put the part in a solvent vapor for a few minutes, and the solvent will condense on the surface of part and smooth out those rough features. And that's basically that the solvent dissolves some of the plastic and turn it into thin skins of the liquid polymer. And after a few time of dry out, you will turns out have the smoothed surface like this. So, but again, that's only for some types of polymers such as ABS, but not for the PLA. All right. So in the previous slides, also in the videos, we see some single color prints. But actually, there are some new developments enables us to print colorful parts like the one shown here. This is a DaVinci color prints. So it can print the white PLA materials, plastic through this fused deposition modeling process. Also, there are different inks to be placed onto the PLA, the white PLA material to produce the colorful parts. And here shows you some of the prints. So let's look at this video to take a look at.
When color broadcasting aired in the 50s, people were blown away by the magic of a full-colored image. And just like with television, the desktop 3D printing industry has been stuck in black and white, but XYZ Printing aims to change that. We bring you the DaVinci Color, the world's first full-color FFF 3D printer, and thus ushering in the new full-color era of desktop 3D printing. Powered by 3D ColorJet technology, the DaVinci Color combines inkjet printing with fused filament fabrication to create full-color prints. CMYK inkjet cartridges drop color onto every layer of PLA filament and are easy to maintain since they can be removed individually. With a hands-free auto-calibration system, motors move the knobs for you so you don't have to worry about calibration. The DaVinci Color also has a robust 7.9 by 7.9 by 5.9 inch build size, and its easy removable print bed allows for easy print extraction. The 5-inch full-color LCD touchscreen interface enables you to navigate through all printer functions. And with Wi-Fi and USB connectivity, sharing designs with your printer has never been easier. Let the DaVinci Color take your design to a new level, allowing creative minds like animators to produce prototypes in true color that are ready to be shown to executives and producers. Character designers to print out their favorite comic book, video games, or fantasy characters in their authentic shape and in full color. Or art designers to give their clients a glimpse of the final product by printing out scaled-down models of their artwork. Bring your creations to life in full color with the DaVinci Color, the world's first full-color fused filament fabrication 3D printer.
All right. Actually, there are other methods which also allows the color printing. That is this mosaic palette. So what it does is it accepts up to 4 different filaments with different colors. Like the one shown here, you have 1, 2, 3, 4 filaments with 4 different colors, and it will cut and splices those filaments and merge them into one single filament, such that it can print the part in different colors. Different regions has different colors. All right, that's how this works. And basically, this could be an accessory for an existing printer, right? You just link this to your existing printer because it only generates the filament for you, right? And by having this, it turns a normal printer into a color printer. So that's another way to realize a color printing. Another advancement is this big area additive manufacturing, in short, BAM, right? So if this process basically is talking about some room level prints, like this house, this car, I mean the car appearance, right? Actually is printed using such a printing process. It's quite similar to the original fused deposition modeling, but it has a large size for the printing area. Also, it usually utilizes the palette, the plastic palette, rather than the filament, right? Because it has a large area for the prints. There's no heat chambers. But the thing is, we just learned how big the shrinkage will affect on a large prints, right? It basically dominates the accuracy of the prints. Also, it could cause curl and such problems. But for such large prints, no heat chamber. So how you prevent the curl? So the solution for such kind of printing process is to use the carbon fiber field in this printing material, in this plastic material. So the carbon fiber will kind of reduce the shrinkage, and to kind of cancel out the shrinkage introduced during introduced by during the printing, because no heat transfer. Again, you have to figure out other ways to prevent the shrinkage, and this carbon fiber filling is the solution. And actually, we have one machine in our Brinkmann lab that is a Titan printer. I believe you have taken a look at it, right, during the lab tour. So it also takes the plastic pellets rather than the filaments, and it also utilizes the carbon fiber fillings to prevent the shrinkage and to improve the strength of the prints. And I would say this kind of printing process, the BAM, is I would say close to the real applications, because you're printing some big part instead of those small prototypings. And actually, the Oak Ridge National Lab invented this printing process, and they are actively working on this to make it more mature towards the a wide adoption in the real manufacturing process, real manufacturing industry. All right. So here show you some of the video for such pallet based machines. Let's take a look at the video. So in this video, the printer is also built by Titan Robotics, which is the same provider of our printer in the Brinkmann. So what the benefit for the pallet fitting is, it has a lower cost because it just utilizes the plastic pallet in the injection molding process, which is very cheap compared to the filament. There are a lot more materials in pallet instead of filament, right? So if we look at the larger size printing, there are more new advancements like the one showing here. Basically, there are multiple nozzles. As you can see here, each of these gantry has one printing head, and they will work together to print a single part. So the software will make sure those kind of printing head will be synchronized, and each of them will print a separate region. As you can see here, each of the nozzle will be utilized for a certain region, and there will be no collision between of them. And the benefit is obvious. Basically, you are speeding up the prints because there are multiple nozzles, not just one. And it's possible to print a larger part in a short amount of time. It depends on how many nozzles you have. And it turns out that will greatly improve the production rate for the 3D printer. But the problem is also obvious. That is how you plan the motion of different nozzle. That's quite challenging. So for the part shown in this video, which is a boat, right? Boat model, that's still simple. But if you're talking about some part with a large area of convex shape, meaning there are many regions pointing downward, then how you separate the model such that these 4 different or multiple different nozzles could work together, that will be more challenging. It's still ongoing research in this area, and there, I mean, still require extensive effort to make it more mature and flexible. All right, I think we just complete the basics of material extrusion process. And in next lecture, we will dive into some details. First of all, some computations in this part. And but before that, let's have 10 minutes break and come back at like 10:05. All right. All right, let's okay. No, I'm not talking about Friday. Okay. Yeah, we can discuss this later. Okay. So what I mentioned is there's no class Monday, which is September 6th, right? That's the Labor Day. We have lectures on September 6th. I mean, we have lectures on Mondays, but September 6th is public holiday. Let me double check on the RIT calendar. Just 1 second.
Okay.
Just 1 second. Let me check. Yeah, there's a no class September 6th. That's next Monday. So the next Monday, there's no class, no lectures. All
Will we
right.
still have lab that week?
That's a good question. Let me think. Yes, I think probably we have lab because the lab actually is has less association with the lecture on that in that week, so it should be fine. There's still some extended content about the fused deposition modeling, so which you have learned in this week, right? So that shouldn't be a problem for the lab. Okay. Yep. Let's. Yeah. Okay. Thank you, Andrew. Okay, let's continue the lectures. Again, we have some calculations about the material extrusions. So first of all, that is this fading systems, right? If we simplify the whole system, it's just like something shown here. You have motors, and the motor will drive the nerd wheel, and this nerd wheel has screw on it, and it pinches the filament and push it into the heated nozzle. And what you need to control is the speed of this spin wheel, such that it will have different speed for the material to be fed into this heated nozzle. So, but how we compute it? So first of all, if we have a known rotation per minute, which of this nerd wheel, then can we come up with the linear speed that the extruded plastic exit the nozzle? Means what is the speed for the material exit from this nozzle, right? And another thing you want to know is this speed for material exiting the nozzle must match the motion of the nozzle over the build platform. I will show you why, but you can just consider this as a constraint or condition. So this material exiting speed from the nozzle should match the speed of the nozzle over the build platform. All right. So of course we need to do reasonable simplifications for solving this problem. So the first one is there's no slippage between this node wheel and the filament, and that will simplify the question quite a bit, because if that's the case, that means the tangential speed at this point will be equivalent to the linear speed of the filament to be fed into this nozzle. And this is reasonable. If there's a slippage, usually that will cause an error during the printing. All right. So another set of parameters we need to know is the diameter of the filament, the diameter of the knurled wheel, and the rotation per minute of the knurled wheel. Also, the diameter of the nozzle diameter of the nozzle, right? So first of all, let's divide this whole problems into several steps. So our ultimate goal, our goal is to figure out what is the linear speed for the material exiting from the nozzle, right? And first of all, let's compute what's the speed this new node will drive the filament to be fed into the nozzle. So let's figure out this first. And basically, we want to compute the tangential speed of the knurled wheel. So how we do that? First of all, let's compute the diameter of this knurled wheel. So its diameter, I mean the not diameter, but the whole the length of the circle, of the whole circle. Basically, you use pi and times diameter of this circle, and then you have this whole length, right? And then we have that's the distance when this narrow wheel travels one turn. So how many turns it has per minute, then we times this revolution per minute, and that is the total distance this node will travel at this tangential point for 1 minute. But we usually, and the final unit is second, then we need to do such a unit conversion here. And it turns out you have the tangential speed of the node wheel in millimeter per second. All right, any questions regarding this? Are we good? Okay. This is very important. You have to understand, and that is this is related to a question in your homework. So make sure you understand it. We have time. I can explain it if you have anything not understand.
Can you just explain what n sub k represents again? Is that the number of, like, is that a number of something?
You mean NK, right?
Yeah. What is that again?
Yeah, that's the revolution per minute. How many turns this circle will be turned for 1 minute? Basically, this is the whole length of the circle, and for 1 turn. But for a minute, there are NK turns. So you have to multiply this to have the total distance. This node wheel travels for 1 minute, and that gives you the tangential speed.
Okay.
Of course, you want to do a unit conversion for this, but that's not the that's not the primary thing. Primary thing is here. You have to understand, well, this is the distance this will travel for one turn, and this is how many turns it will rotate for 1 minute. Then multiply them together, you have how many what's the distance this will travel for a minute, right? Turns out it is the speed. Then change it to millimeter per second, and that's it. Okay, any other questions? Are we good? Okay, let's move on. Now you know basically what's the speed this this filament to be fed into the nozzle. Then the question will be, what is the speed for the material exiting from this nozzle? And you have to understand one thing is, we assume, and this is true, that how many material get into this nozzle should be equivalent to how many material exits from the nozzle. So in that sense, the unchanged thing is the volume of the material. In the inside, the material into this nozzle should be equivalent to material outside of the nozzle. And what we can compute is the volumetric flow rate. So this is also equivalent, invariant from at the for the input one and the output one, right? So then we compute this volumetric flow rate by using the area times speed. So the area is the area cross-section area of this filament, right? The speed is the speed we just computed from the previous step. Let me clean this up. It's a little messy. So this is the speed of the filament moving, right? And we just directly use it here. And then we also have the area of the filament, because dF is the diameter of the filament, and we just use this equation to compute the diameter, the area of the cross section of the filament, and time the two together, you have the volumetric flow rate. And this flow rate is invariant, means the one inside this nozzle is equivalent to the one outside of nozzle, right? So use this, you can come up with the linear speed for the material exiting nozzle, and I will show you how. So remember, you have this, right? Oh, for this step, any question? Okay, let's move on. As I mentioned, the flow in should be equivalent to flow out, and you have already come up with the flow in the previous step, right? That is what you have, and you can directly put it here, and then how you compute the flow out. So for the flow out, again, it is the cross-section area of the nozzle times the linear speed of the material exiting from the nozzle, which is what we want. This way out is what we want. And this cross-section area can be calculated using the diameter of the nozzle. And it turns out this number can be calculated by move this part to the left-hand side, right? Just over, this part over this part, right? Turns out you have the velocity. Let me again do little cleanup. All right. So for this one, for this part, any questions? No? Yeah, I think that's if you follow the steps, it shouldn't be difficult to understand, right? And basically that's this V out is our looking at, right? That's the material speed for exiting from the nozzle. Sometimes the volumetric flow rate and the cross-section area of the nozzle is given, then you can directly have the V out instead of figuring out from the very beginning, right? That's the simpler cases. But no matter how it should be fit into such a process, right? To find all the necessary information and find out the unknowns by using the known information. So you might ask why we want to match the plastic exiting speed with the nozzle linear motion speed over the platform. So here is the reason. Because if they are not matched, you will have this kind of case or this kind of case. So if it moves too slow, the extruded material will pipes up and the nozzle and get smeared. Sometimes some extreme case is you have a really large pile and it turns out it has collision with the nozzle and prevent the whole process. That happens in last spring semester. There's a printer basically has such case, the material piled too high and it collide with the nozzle, and I have to actually I have to purchase another set of hot end and replace the whole hot end. That's really terrible, but you should understand what is the cause, because the nozzle moves the speed of the nozzle movement over platform is not matched with the plastic material exits the nozzle, right? So in the opposite case, if it moves too fast, so that means you could miss some plastic material in some regions like the one showing here. It will break and produce gaps in the prints, which is also undesired because that will essentially make the strength of your prints not reach the requirement. So these two cases are not are undesirable and should be prevented. So another computation related to the energy, the heat. So basically, here is the equation gives you how much energy is required to complete the prints. Essentially, you will know these temperatures. As you can see here, Tm, TO, TP, and Tm. So the Tm is the melting temperature of the material. TO is the starting temperature. And TP is the printing temperature. So during the process, the filament material is heated up from its starting temperature, usually the room temperature, right, to the melting temperature. And then the material is heated up further to reach the printing temperature. So you can think of the melting temperature basically is the division of the material in solid state and liquid state. And after the melting temperature, the material is in liquid state, but still require some heat up to be ready for the printing. So that's why there are two sections here. Basically, this portion represents the temperature raising from room temperature to melting point. And this part gives you the material, the temperature increasing from the melting temperature to the printing temperature. And this CS and CL gives you the specific heat capacity of solid and liquid material. And besides these two, there is another term HF, and that is the heat of fusion. So during the printing process, there will be some heat required for the fusion of the material. And this part need to be considered as well. And together with the three terms, you have the mass over here, where rho is the material density and V is the volume of the material, part volumes. And put them together, you will have the overall energy for this printing process. So I know it looks like very complex, but if you understand each of the term, it becomes much simpler, right? But you need to understand the whole process for this printing, right? From the room, the starting temperature to a melting temperature, and from the melting temperature to the printing temperature. Also, there's a heat of fusion, and that's what are the three terms for during this process. Any question for this? Okay.
Professor.
Yeah.
I asked in the chat, and so in quizzes or tests, will we ask mathematical questions using this formula or related formulas?
Yes, there will be questions. Yes.
Okay, thank you.
Yeah, that will be definitely one or several questions related to this. And if you ever taken my course, you will know I will give the equations to you. I will not let you memorize it. So you will have these equations. The only thing you need to do is understand it and know how to use it, right? But I can assure you this will be one of the questions. All right, let's move on. So if we have a printer, right? And let's assume there's no loss of heat from conduction, convection, and radiation, means there's no energy lost, right? And now let's decide what will be the watts are necessary to heat a printing process with 1.75 millimeter diameter PLA filaments. Also, you want to print your part at 50 millimeter per second with a 0.5 millimeter diameter nozzle. If you look at, if you look at this, you might feel confused, right? So basically, that combines what we have gone through for the previous few slides. The two questions. One is the speed of the material exiting the nozzle Another one is the energy required for the printing process. So how we combine them together to solve this question? Let's look at them one by one. Again, kind of divide the whole problems into several sub-problems. Then you have easier solution, right? For each of the sub-problems, and then put them together. So one important thing I want to mention here is for such kind of question, a necessary step is to make the units consistent to each other. For example, for these ones, you have gram per cubic centimeter, you have gram per K, and more per K, or so on and so forth. And you definitely want to make them consist. Otherwise, there will be an error introduced. So for example, basically the temperature K is your the Celsius degrees plus 273, right? Then you have the conversion to it from the K to Celsius. Another one is gram per mole. What you want to do is there are different, basically for different material, there will be different molar mass. And for example, for PLA, it has 80 gram per mole. And therefore, for this heat capacity, basically it is joule per mole per K, right? So what you want to do is you just times 1/80 gram per mole, and it turns out you will have this converted to gram instead of mole. So you convert this unit to this one, right? And that's how you could solve this unit conversion. So that's very important. If when you solve a question, that's probably your first step to make sure these units are consistent to each other. All right. And then we look at how you solve this question, right? So the question is asking you the watts instead of the energy joule. So basically what you want to do is you want to have the energy per unit, and that is the watts, joule per second. So you want to divide both of the two by the time t. I think the right handwriting is something. Let me redo the writing. If you over h over t, and here over t, basically you divided by, you have the both two sides divided by t, then on this side that is the watts, and then you want to figure out this instead of the one without divided by t, right? So that's the difference between the question and this equation. So therefore you want to have the volumetric flow rate instead of the volume. To compute the volumetric flow rate, what you want to do is first figure out what is the cross section of the nozzle, right? The cross section of the nozzle, cross section area of the nozzle, because the diameter is this, then the cross section area can be computed in this way. All right. And what is the linear speed this flows. Actually, this is given 50 millimeter per second. And easily you can compute this volumetric flow rate by substituting this to this equation. And that is the volumetric flow rate, which is essentially V over T. And once you have V over T, the rest will be substitute this, what you just come up with to here, and substitute C, CS, TM, T0, HF, CL, TP, and TM. And it turns out you have this 4.94 watts, right? That's how you come up with this this power, right? Another tip is for the temperature. See this Tm minus T0 and TP minus Tm. So because the Kelvin, the temperature in Kelvin is just a Celsius plus a constant 273. So for this subtraction, there's no difference if you use Kelvin or Celsius. The only thing is you have to make them consist, meaning if Tm and T0 are all in Kelvin or all in Celsius, there's no difference for their for this subtraction. Same thing happens here, but definitely you want to make them the two in the same unit, either Kelvin or Celsius. All right, that's a very important part you want to keep in mind when you do the computation. So any question for this one? Okay, there will be a question related to this one. And basically there will be some variations because what we just compute is based on the assumption there's no energy loss. So what about there is energy loss, which is the real case in the real situation for the real printer, there's definitely energy loss. Let's see, there are 50% of the energy lost. Then will this still work? Will this power still work? Then you should be able to figure out what are the real energy, what are the energy really used for the printing process, and whether the provided power is high enough to provide such energy, because there are portion lost. Then you need to compare compare the provided energy, the power, versus the required power plus the energy loss, right? That will give you the idea whether the provided power is large enough or not. In some homework question and exams, there could be some question like this. All right. So any questions again for this? Okay, let's move on. I think we can talk a little about the materials. Just 1 second. Let me open another slide. All right, just. So for the materials utilized in the material extrusion, basically there are two different types. If you ever learned material processing or other manufacturing related courses, you should know there are multiple types of plastic materials. And the most widely used one is the thermoplastic. And another also widely used one is the thermoset. And the major difference between the two is after the soften or the melting of the material, thermoplastic can be remelted. But for the thermosets, cannot be resoftened and remelt. So that's the primary difference between these two materials. The reason is if you look at their chemical equations, you should understand basically in the thermoplastics, there are different types amorphous, crystalline, semicrystalline, or elastometric. And both of them could be melted and remelted numerous times, but the mechanical property would degrade with each heat cycles. So you cannot infinitely remelt and resolidate the thermoplastic without the loss of material property. And the chain, it has organic compounds like these elements shown here. So basically that is how it looked like in the mechanical chain level, right? I mean the chemical chain. And so what are difference between the amorphous and the crystalline thermoplastic? So if you look at their this illustration here, for the amorphous, so basically its molecule chain is something like this. It's like a spaghettis, right? And it's a little messy and has no pattern over there. But for those crystalline or semicrystalline, you will see these well-structured patterns, right? That's the major difference between the two type of thermoplastic material. Another interesting material is the elastomers, like the one we could use in our prints is the Ninja Flex or the Fila Flex. So we call it TPUs. So if we look at the molecule chains of these material, if the material is in the release state, you can see these unstretched molecule chains. But if there's a force applied, basically you are stretching the material. These chains are stretched as well. So that's why it has a flexibility for the printed parts. And for the thermoplastics, there are some very important temperatures. For example, the glass transition temperatures. And below this temperature, the polymer is relatively hard, brittle. And above it, it becomes soft and flexible. And this glass transition temperature is only applicable for the amorphous thermoplastics. Also, the crystalline temperatures. So basically, if the temperature is above this crystalline temperature, the polymer will transit from the amorphous polymer chain to the organized crystalline structure. Like basically, if you look at this, right, basically it will transit from this one to something like this, right? But not all the polymer will crystallize. So that's there are some assumptions like styrenes, right? Another very important one, the melting temperature. The melting temperature, if a temperature is higher than this melting temperature, polymer will become a liquid state. Actually, only the crystalline thermoplastic melt. That is one thing you want to keep in mind. For the amorphous ones, it doesn't actually melt, right? Just keep this in mind. So here I show you some of the plots for these temperatures, the crystalline temperature, glassification temperature, and melting temperature, right? Also, there's a relationship between these temperatures versus the heat flows. At the glassification temperature, this heat rate increase. And you want to find out the midpoint between this increasing part, right? That's the glassification temperature. And if you want to find the crystalline temperature, basically just find the drops, the first drop of the curve. And this melting temperature is at the highest point of the heat flow rate, right? That's how you figure out these important temperatures by looking at a differential scanning calorimetry result plots, right? All right. So in the as I mentioned, the thermoplastic is the most widely used one in the material extrusion, and many of these filaments in using a thermoplastic is heated above its glass transition temperature or the melting temperature, and pushed through a nozzle. So for different material, there are different such a temperature. I mean, the glass transition or the melting temperature. And that's why you need to set up different temperatures. And different types material like PLA, ABS, TPU, polycarbonate, and Ultem. These are the primary ones you want to take a look at it. There are forms and charts with all those temperatures listed when you have material provided. And based on that, you should be able to set up using the software, right? And also there are other types like composites material, and that will be a different story because those temperatures will be quite different from those pure plastic material. So there are some other material added to the plastic material, like some of the plasticiers. So these are some compounds added to the original plastic material for lowering the glass transition temperature and increase the flexibility of the part. Also, there are some material which is added for prevent the flame or stabilize the material to prevent the possible degradation from the environment factors such as UV or oxidation, and so on and so forth. I mean, oxidation. And these are the add-ons, and these add-on materials could change the temperature, those temperatures, glass transition temperatures, crystalline temperatures, also the melting temperature. And you need to look at their descriptions, usually with the material, with having these add-ons, there will be some special explanations from the provider, from the manufacturer of the material. And that will tell you how you handle the material. So for the filaments, the moisture absorption could be a problem. So if you look at what we have in the lab, especially for the nylon material for the Onyx machine, what we usually do is we keep them into a closed box instead of let them to be exposed to the air. The reason is these plastic materials will absorb the moisture, and that will introduce problems for the printing. So just imagine if you have moisture in your filament, when the filament is heated up, the moisture is boiled, and it could generate bubbles. And turns out that will leave some empty void space in your printed part, which is undesirable. That's why you don't want to have your filament to be exposed in the air for a long time, and that's the reason. Here gives you some of the material property chart for the ABS material. Again, this kind of figure shows how I mean the primary materials usually used in 3D printing, and basically it integrates all different material properties and temperatures you want. So some other properties which is important, for example, the heat deflection temperature. So basically that is the temperature at which a polymer sample deforms under certain load. For if you look at the heat deflection temperature test, there's a load applied to this beam, right? And when temperature increases, this beam will be deformed, and the deformation, how much it deforms, will be recorded for this heat deflection temperature, right? And also there's another important property, which is the coefficient of thermal expansion. That is for describing the material length change per degree change in temperature per unit length. For example, if you look at this, the original part will be, the dimension of the original part will be changed if the temperature is changed, and this difference will be length change, dimension change will be recorded, and as the coefficient of thermal expansion. So related to the material property, there's a post-processing which is called the thermal annealing. So this thermal annealing is a post-processing to increase the strength and mechanical property. So basically what it does is heating up the part in an oven to relieve the shrinkage stresses in the part and to crystallize the material. And if you look at the molecular chains of the material, if you have a recrystallized form, you can see the patterns are more organized, uniform. So it turns out that leads to a better mechanical property. For example, we have our Markforged Onyx material, and there will be a increase of the ultimate tensile stress after this thermal annealing, and the yield stress increasing. Also, the stiffness is increased. But there's one thing decreased, that is the impact energy at a break degrees. That gives you some idea that it might decrease the, it make the part brittle, rigid, I mean higher stiffness, but more brittle after this process. That's why you have this impact energy at break decreases almost a half, right? So I think that's pretty much all for today's lectures. And I will release the first assignment, and you can hand in your assignment next Tuesday. And I will also release this recorded lectures as well as the 2 lecture notes. Basically, what you need for solving the homework questions will be on the lectures. Yep. I think that's pretty much for today's lectures. Any question?
Yeah, hi, it's me again. I have one last question.
Sure.
So on one of the, I have lab section on Fridays,
Yeah.
and I know for sure that I'm going back home to New York City within like the next few weeks, in which case I won't be able to attend like the lab for that week. So I want to know, like, is it possible that I can just like slide into like the Wednesday section for that week and just communicate with my partner, like, you know, what it is that I've done for the remote control car project or something like that?
Well, that's possible, but you have to have the permission from the TAs. Basically, contact the TAs for their to see their convenience or their arrangement. I mean, usually we do not do such kind of change, right? Because I mean, we need to make sure the everybody has a chance to operate the printer. But since we have less people per session, so that becomes possible. But the thing is, you need to contact TAs to
Okay.
arrange it.
I'll do that. Thank you.
Okay. Any other questions? All right. If there's no more questions, that's the end of the class. Yeah. Where is the homework? So that will be posted on my courses. I will create a menu under the content, which is called homeworks. You can find the homework question there. And you can upload your completed homework to the Dropbox on the my courses as well. I will start a session there. So the due will be next Tuesday. All right, next Tuesday, that which is September 7th. Any other questions? All right, that's pretty much all for today's class. Okay, take care, guys. See you.